I mentioned last lesson that there are a couple driving forces for reaction spontaneity, things that will work to make a reaction occur spontaneously or not. And one of those is entropy or disorder. So entropy, symbol for entropy is S, capital S, is a measure of the degree of randomness or disorder in a system. And I've seen it in other resources that entropy is a measure of the dispersal of matter, however you want to take that. So we're going to look at it in terms of randomness or disorder. So we said that nature favors processes where what you end up with are more disordered than what you started with. Nature favors processes where uh, randomness increases. Let's take a look at an example here. Let's say you have a two-chamber container and you have two gases in that container. So let me draw a picture and show you what I'm talking about. So let's say we have a valve here in between the two chambers of this container. And let's say we have two gases, gas X and gas O. And let's say that we start off with them in the left chamber of this container. So if we were to open up this valve, let's see if I can do this. There we go. What are the different ways that those particles would arrange themselves in that two-chamber container? Go ahead and pause the video and see how many different setups you can come up with in terms of where the gas particles are in this two-chamber container. Go ahead and do that now. So here are the different combinations of arrangement of particles in that container. Both gases could be on the left side, both gases could be on the right. Gas X on the left, gas O on the right, or the opposite of that. So again, this is just based on random particle motion and where those particles may be at any given time, or the different combinations of where they may be in that container. What if we had three gas particles still in a two-chamber container? So I'll start off with the first picture. So this time we'll call them gas X, gas O, and gas delta, or triangle there. So one arrangement would be that all three gas particles are in the left chamber. Go ahead and pause the video and see how many different combinations of arrangements you can come up with. Go ahead and do that now, please. Did you come up with 8 different combinations? So here they are. We have, again, all three gases on the left, or the opposite of that, all three gases on the right. Gas X and gas O on the left, delta on the right. Gas X and delta on the left and O on the right. O and delta on the left, X on the right. Delta on the left, X and O on the right. O on the left, X and delta on the right. And X on the left and O and delta on the right. Hopefully I didn't get any duplicates here. And hopefully that's all of them. So you can see as the number of particles increases, we have a greater number of possible arrangements of those particles inside this container. So that'll be important in just a little bit. So as we mentioned before, say it again, changes where the products, what you end up with in a chemical reaction, are in a more random or disordered states are favored. They're likely to occur by themselves. The reason is that it is simply more likely that way. So things just tend towards a more disordered nature. Let me give you an example of this. Here's a little cartoon proving that nature favors disorder. Now let me ask you this. Who of you has a messy room? I would probably guess that a lot of you have a messy room. Here's another question for you. How much effort does it take to have a messy room? It takes no effort at all. The room gets messy all by itself. Some of you perhaps have a clean room. How much effort does it take to have a clean room? Well, you have to actually do something to have a clean room, whereas you don't have to do anything to have a messy room. Nature favors disorder. So technically, it is not your fault that your room is messy. It is entropy. Now, something to be careful of, don't go home and tell your parents that your room is messy because of entropy. Because as a parent, what I would tell my kid is, I don't care, go clean your room. But it is true, nature favors disorder. All right, so what we're going to do is we're going to look at the changes in entropy that occurs during some chemical process. And so there's certain things that we can look at in terms of what we start off with and what we end up with that will help us to determine if entropy is increasing or decreasing. All right, so let's start with the states of matter. You'll want to look there first, especially if you're looking at, say, a phase change that's occurring, whether a substance is melting or freezing or boiling or condensing, and make sure this makes sense. Of the three states of matter, solids have the lowest entropy. They are the most ordered or least disordered. The particles are arranged in a highly organized fashion. There's a picture of this, actually a couple pictures in your book, page 697 at the top. We show what's being shown there is a process of melting of gallium metal. So we start off with the solid particles, again, nice and ordered and arranged in a certain way. And then that substance rather turns into a liquid. Particles are a little bit more disordered. They're still touching each other, but they don't occur in a repeating pattern. And so we say that liquids have more disorder than solids. And then looking at the next example, we see evaporation, where we take a liquid and turn it into a gas. Gases have the most disorder. The particles are all over the place, random arrangements, moving around constantly. And so gases have much more entropy than do liquids. We could also, in this list, put aqueous. I know it's a little bit later in the notes, but where do you think an aqueous solution would fit in this hierarchy of disorder? Pause and think about that for a second. So if you said that aqueous solutions would be here, maybe between liquid and gas, that would be correct. So again, if you're taking, I don't know, a solid, and then you're dissolving that in water to make an aqueous solution, entropy would be increasing. You're going from solid to aqueous. So that's one of the things we can look at. And it doesn't have to be a physical change. It could be a chemical change. So if you start off with some solid that undergoes a chemical reaction where you make a gas, let's say, then you're starting with a solid, you're ending up with a gas. Gases have more entropy than solids, so we would say that entropy is increasing. Some other things that we can look at are temperature. So because the particles of a substance are moving faster at a higher temperature, this leads to a more disordered arrangement of the particles. So a substance at a higher temperature has a greater entropy than a substance at a lower temperature. And as we saw with the example at the beginning, if you have more particles, there's just more possible arrangement of those particles inside the container, more disorder. So if you have a situation where you start off, say, with 5 moles of gas and that turns into 10 moles of gas, we would say that entropy is increasing. And lastly, if we're comparing individual particles, so S is known as absolute entropy. Every substance has a value for S, including elements. The only time the value for S, the absolute entropy of a substance, is 0 is at absolute 0. And so if you recall that the values in the back of your book are for substances at 25 degrees Celsius. So every substance has a value for S, or absolute entropy. And when comparing individual particles, larger molecules, because they have more protons and more neutrons and more electrons, more subatomic particles, have a higher entropy than smaller molecules. This is true for individual atoms as well, so it doesn't have to be molecules, could be atoms too. Take a look on 696. Again, here's another example. You take graphite, which is a form of carbon, and react that with water. So graphite is a solid, water is a liquid, and you make carbon monoxide gas. So you're taking a solid and a liquid and you're turning that into a gas. We would definitely say that this system is becoming more disordered and entropy is increasing. Like I said, figure at the top of page 697, we looked at melting and evaporation already. Take a look at what I was talking about before, dissolving. So you take a solid solute. We see the organized arrangement of particles in that solid represented with the red spheres there, red circles. And then you dissolve that in a liquid, and what you end up with is a mixture. And so look, it looks to be that that mixture has a much higher degree of disorder than do the solid and liquid by themselves. And it looks, I think I missed one here. Number 3, sorry about that. Mixtures, and we can see that here in that example. Mixtures have more entropy than solids or liquids or any other pure substance, unless it's a gas, I suppose. All right, something that we need to answer these book questions is this. We're looking for whether or not entropy is increasing or decreasing. And so technically, anytime we're doing problems involving this, we're looking for the change in entropy that occurs, delta S. And so make a note, if entropy is increasing, the sign for delta S is positive. And if entropy is decreasing, the sign for delta S is negative. So what we want to do here is we want to look at each of the processes that were given in this practice problem, number 12 and 13, and determine if entropy is increasing or decreasing, and as a result, the sign for delta S being positive or negative. Be prepared to explain to me why you chose either positive or negative for each of these questions. All right, go ahead and pause the video and work on that now. All right, letter A, we're going from sugar dissolving in tea. So we have a dissolving process. We're starting with a solid, turning that into a mixture. I would say that entropy is increasing, therefore the sign for delta S is positive. Letter B, frost forms on a window pane. So we're going from, I suppose, liquid or gaseous water to liquid or solid. Frost is ice, basically. So the water vapor in the air is turning into ice on a window. Maybe something that you're not familiar with because it doesn't get super cold here. Nevertheless, you're taking something and you're turning it into a solid. Solids have the lowest entropy of any state of matter. So it doesn't matter if you're starting with a liquid or starting with a gas. If you turn that into a solid, entropy decreases. Therefore, the sign for delta S is negative. Letter C, air is pumped into a tire, so you're adding more particles. More particles have more entropy than less particles. So once again, the sign for delta S is positive. Letter D, acetone, which is a liquid, evaporates from nail polish remover. So we have a process of taking a liquid and turning it into a gas. Anytime you take any substance and it turns into a gas, no matter what it starts with, because gases have the highest entropy, entropy is increasing, sign for delta S is positive. Number 13 is a little bit different. We're given a chemical equation. So we have chemical reactions that occur versus in number 12, those are all physical changes. So remember that your book uses the CR for solid, L for liquid, G for gas. So we start off with solid calcium carbonates. You turn that into solid calcium oxide and gaseous carbon dioxide. So it doesn't matter that there's a solid that's produced. What I see is you start off with a solid and you turn that into a gas, even though there's a solid, a different solid that forms, doesn't really matter. You're taking a solid and you turn it into a gas. Entropy is increasing. Sign for delta S is positive. Letter B, everything is a gas. So we can't answer this question based on the state of matter. So anytime you have all of these substances involved in the process in the same state of matter, look at the number of particles. So we start off with 4 moles of particles, and we produce 2 moles of particles. So the number of particles during this process is decreasing. Less particles have less entropy. Therefore, the sign for delta S is negative. So that is how we qualitatively determine change in entropy during a chemical process. Let's quantify it. How do we calculate actual change in entropy that occurs during some process? Well, we can use this formula. And again, I'm going to use this symbol, so delta S of reaction, change in entropy of the reaction at standard conditions. And very similar to how we can calculate delta H for a reaction using delta HFs, we're going to now this time use the absolute entropies. So we take, of course, the number of moles of the substance times the entropy, so entropy of some of the entropies of the products, minus the sum of the entropies of the reactants. Now, as I mentioned, these values, absolute entropies, are given to you in the back of the book. So just like we did with delta HFs, we can do the same thing with absolute entropies and calculate the change in entropy that occurs during a chemical reaction. Now, it should be noted that where delta H's in the back of the book are given in kilojoules per mole, absolute entropies, S, are given in joules per mole Kelvin. So that'll be important later on. Once again, what's important for now is that we have a value per mole, and that's why we want to multiply the absolute entropy of each substance by its coefficient in the chemical equation. So in the last lesson, I had you calculate the delta H, heat of combustion, for the combustion of 1 mole of methane gas. This time I want you to calculate the change in entropy, delta S, for the combustion of 1 mole of methane. So go ahead and start off with the balanced equation for the reaction. Go to the back of the book, find the absolute entropies of each of the substances involved in the reaction. Apply products minus reactants, and you should get your answer. I think this time, go ahead and use the values exactly given to you in the back of the book. I don't want you to round those to 3 sig figs because there's something we're going to do later on. So take those values as given in the back of the book. Be careful with the precisions. We're adding numbers up, and so we want to be careful to give our answer to the correct precision based on rules for significant figures when adding and subtracting. Go ahead and pause the video, set that up, and see what you get. All right, so here is our setup. So this is the absolute entropy of carbon dioxide, 213.74 joules per mole Kelvin. This is the absolute entropy of gaseous water vapor, and we have 2 moles of water produced in this reaction, and so we need to multiply the value by 2. This is the absolute entropy of methane, and then we have 2 moles of oxygen gas. So we're going to multiply the absolute entropy of oxygen by 2. Products minus reactants. Now let's look at the equation. Everything is a gas, and we have 3 moles of gaseous reactants and 3 moles of gaseous products. Is the entropy increasing or decreasing? It's kind of hard to tell here. It's hard to predict. So that's why quantifying this will be better in this case. So we end up with negative delta S, so that means that entropy is decreasing, but it's really small, 5.150 joules per mole Kelvin. Again, why is it 3 digits after the decimal? Actually, I think it should be 2 digits after the decimal, right? We have our least precise number there is 213.74. So I was just copying my notes from earlier. So this might be a better answer. We'll want to talk about this in class. I think that should be good. Negative 5.15 joules per mole Kelvin. All right, that concludes this lesson. Next time we'll talk about delta G and how we can use delta H and delta S to predict if a reaction will occur spontaneously or not. Thanks for watching.